Hi everyone, so in this video we will explore the notion of what does it mean for two sets to have the same cardinality. So this might be pretty clear for finite sets that have finite number of elements in them. We'll see how we can extend this to sets that have infinite amounts of elements in them, and are all infinite sets created equally? So are there different levels of infinity? And we'll explore that idea a little bit more in class together. So let's first think about the definition, about what it means for two sets A and B. And for now, we can think about these sets as having a finite number of elements for these two sets to have the same cardinality. And so one informal way would be to say, well, they have the same number of elements in them, so we can count them up. This set has 5 elements. This set has 5 elements. They have the same cardinality, but we want to extend this to infinite sets as well. So we want to extend this same definition of same cardinality to infinite sets. So we're going to tweak that definition and just say two sets have the same cardinality if there is some bijection from set A to set B. And again, what this means for a bijection is it's injective. So every element has their own unique output, and it's surjective, so that every element in the codomain B gets mapped to by some element in the domain A. So let's take a look at some examples below. So first of all, let's consider the set A, which has 2, 4, and 6, 3 elements, and set B also has 3 elements. So we don't need a fancy definition to say, yeah, A and B, they both have 3 elements, so they have the same cardinality. But we can do this more formally by introducing a function f, which is a bijection that maps from A to B, where each element in A, we add 1, and that gives us the element in B. And so in this case, we have a nice formula for describing how exactly we're going to match each element from A into B. We could have just written out this set element by element as well. Okay, so one more example. Let's say we have a set F of these 4 power functions, and I have a set G of these other 4 power functions. Okay, each set has 4 elements, so they have the same cardinality, but we could define a bijection, we'll call this one R, from set F into set G, where we just subtract 1 from the power. And x would therefore go to x to the 0, which is 1. X squared would go to x, x cubed to x squared, x to the 4th to x cubed. Okay, so you might be thinking, why can't we just define this as saying we're going to count the number of elements here and the number of elements here? And if they're the same, then they're equal. Well, this idea wouldn't be able to be extended to infinite sets, since we can't count up an infinite number of things. So let's see how this might work with infinite sets. Okay, so first of all, let's define what it means for a set to be infinite. We say a set is infinite when it is not finite. So it's much easier to define what it means to be finite. We can count the number of elements in S, and that adds up to something which is finite. And so we'll just say that if we can't do that, then the set is infinite. So let's see how we can compare cardinalities of infinite sets with a couple of examples. So first, let's let E denote the set of all even integers and O the set of all odd integers. So each of these sets is infinite, and we might think, are there the same number of even numbers as there are odd integers? And so, yes, there are. You probably believe that. And here we can construct a map that actually explicitly shows how we can take each element in E and map it to an element in O. So here we've got A going to A plus 1. If A is even, A plus 1 is odd. And we can prove, probably we should prove, that this is indeed bijection. So this definition of two sets have equal cardinality if there is a bijection from one into the other still holds even when we have infinite sets. So here we could say the set of even integers and the set of odd integers have the same cardinality. And for another example, if we take the set of all natural numbers, and now we consider e plus the set of all positive even integers, then we can define a map from the natural numbers into e plus by taking each natural number a and mapping it to 2a. So this means we would get 2, and then 4, and then 6, etc. So you might have thought, well, e plus is actually a subset of the natural numbers, and that's true, it is, but both of these sets, we would say, have the same cardinality. They have an infinite number of elements, and we'll see that that notion of infinity is the same in both of those sets. And one last example that we will explore more in class is, well, you could also think, what about the natural numbers and the real numbers? The natural numbers are a subset of the real numbers. They both have an infinite number of elements in these sets. So can we come up with a bijection from n into R? And the answer is that there does not exist a bijection. And we will prove this together using contradiction. But since there is no bijection from n into R, then we would say that n and R don't have the same cardinality. So n has an infinite number of elements, R has an infinite number of elements, but it's not the same type of infinity. And so we can classify these different types of infinity into two categories, and we'll define those two categories in the following way. So we'll say that an infinite set A is called countably infinite, or it might be called denumerable. These are used interchangeably if it has the same cardinality as the natural numbers. And so what that means is there should be a bijection from the natural numbers into A. And so if we can construct this bijection or show that one exists, then we would call set A countably infinite. And more generally, we say that a set is countable if it is finite, so all finite sets are considered countable, or if it's countably infinite. And a set which is not countable is called uncountable. So let's take a look at some examples. So clearly n is countably infinite because we can find the bijection from n to itself. On the previous slide, we showed that there was a bijection from n into the positive even integers. So therefore, we could say e plus the positive even integers are also countably infinite. And lastly, we will see in class together that the set of real numbers R is not countably infinite. So therefore, we say that the real numbers are uncountable, since it is not countable. It's not finite, and we'll show in class together that there does not exist any bijection F that goes from the natural numbers into R. So the real numbers are actually more real numbers than natural numbers, although there's an infinite number of elements in R and in N. The infinite number of things in R is a larger infinity than the infinite number of numbers, natural numbers. And we'll see this in class. We'll explore this idea in class together.